So in this chapter, we're talking about the different states of matter. The first one we're going to be discussing is the gaseous state, so how gases behave. And the way we treat a gas, generally when we talk about gases, is as an ideal gas. And so with an ideal gas, there are certain rules that we follow about how a gas behaves. So it's the model that we use when we're describing or calculating properties of gases. And we'll talk a little bit about those uh, characteristics of an ideal gas later on. But just for example, some characteristics of an ideal gas. So gas molecules are not attracted to one another. So they're not. So as they're moving through the container, they don't attract to one another or repel one another. Another one is they move in straight line, random fashion. So they just keep on moving until they hit the wall of the container, and then they go into another direction in straight line fashion. And that the volume of the actual gas molecules make up very little of the volume of the container. So we assume that the volume of the container is the volume of the gas, because the gas molecules make up a very small portion of it. So those are just some of the characteristics of an ideal gas. Now for a gas, we can measure one of four properties. We can measure the temperature of the gas. And for temperature of a gas, this is very important. It's measured in degrees Celsius. But calculations use Kelvin. So anytime you do a calculation in this chapter involving gases and you're using temperature, make sure it's always in Kelvin. That's a must. Volume, you can measure the volume of a gas, and the general units of volume that we use milliliters and liters. But for some equations, like the ideal gas equation, which we'll talk about in a little bit, can only use liters. So there are some restrictions on the types of units you can use depending on what type of equation you're using. So if we use the ideal gas equation, volume has to be in liters. We can measure the pressure of a gas, and we'll talk more about what pressure is in just a little bit. But pressure is generally measured in millimeters of mercury, torr, or atmospheres. But for calculations involving the ideal gas equation, pressure needs to be in atmospheres. So whenever you use this ideal gas equation, you got to make sure that you convert your pressure into ATM. And we'll talk about how to do that in just a little bit. And then we can measure the amount or mass of a gas. And with the mass of a gas, when we're measuring it, when we use it in calculations, we use moles. So whenever you're going to talk about the amount of a gas, we're always going to convert it to moles. So we generally deal in moles. Now what we're going to see here in a little while is how each one of these properties of a gas are interdependent on one another. So for example, at a constant pressure, how do volume and temperature relate to one another? At constant temperature, how does pressure and volume relate to one another? So we're going to see how they're interdependent on each other. And so we'll be looking at the different relationships between moles of gas and volume, for example, volume and temperature, pressure and volume, and see how all of these relate to one another. So for example, as we increase volume, how does temperature react? Does it increase or decrease? As we increase volume, how does pressure react? Does it increase or decrease? If we increase volume, how does the moles of gas react? Does it increase or decrease? So we're going to be talking about these individual gas laws and their relationship to one another. Now, the mathematical term for pressure is the amount of force per unit area. But the way we illustrate pressure in chemistry is the molecules colliding with the walls of the container. So the molecule has some force. It strikes a certain area of the container. That's where the force per unit area comes from. But it's as these molecules hit the container, they cause pressure. And so as more molecules hit the container, your pressure increases. So that's what gas pressure is. It's the result of these molecules hitting the walls of the container. And the way we measure pressure, at least atmospheric pressure, is by using a barometer. And so what a barometer is we have a pool of mercury. So this right here is a pool of mercury, because mercury is a liquid metal. And as the atmospheric pressure presses down on the mercury, it causes it to rise in a tube. And as it rises in a tube, there's actually graduations on the tube, most commonly millimeters. And however high the mercury rises, we record that pressure as millimeters of mercury. And so that's where one of the common units that we use in pressure comes from. It is millimeters of mercury. It's how high the mercury has risen, and measuring the height in millimeters. Some other common units are atmospheres. Torr is the same thing as millimeters of mercury, except torr is at other temperatures other than 0 degrees Celsius. Pascal is another common unit. Now, one thing you need to remember is that 1 atmosphere equals these pressures. And so these are going to be the conversion factors for converting from these units of pressure to atmospheres. So the way we would write this is that 1 atmosphere equals 760 millimeters of mercury, 1 atmosphere 760 torr, and 1 atmosphere 76.07 centimeters of mercury. So these are all the equalities to convert between atmospheres and those different units. So to give you an example, let's say we have 960 millimeters of mercury and we want to convert it to atmospheres. So we'll set up our train track. And so on the top goes the millimeters of mercury. Now we're going from millimeters of mercury to atmospheres. So in our conversion factor, millimeters of mercury goes on the bottom, and atmosphere goes on top. And so if we divide 960 by 760, we get the number of atmospheres in this many millimeters of mercury. That's about 1.26 atmospheres. So that's how we convert between millimeters of mercury and atmospheres. But let's say now we want to convert 2.3 atmospheres to centimeters of mercury. And so we see that 1 atmosphere is 76 centimeters of mercury. So we're going to set up our train track. And we're starting with 2.3 atmospheres. And so 1 atmosphere goes on the bottom because we're starting with atmospheres, and then 76.0 centimeters is on top. So now when we do this, we multiply, we get 175 centimeters of mercury. That's how you interconvert between the different units of pressure. Now, you don't have to memorize the actual equalities, you just have to know how to utilize these equalities. So some properties of gases that we need to discuss is that you can compress a gas very easily. So if you have a sealed container, you can decrease the volume, causing the gas to compress. Now, as we said, for ideal gases, we assume the gas is mostly empty space, and therefore, since the particles are far apart, it's very easy to compress the gas. The gas will fill any volume of the container, so whatever volume the container is, the gas will fill that. Now, since these are ideal gases, there's very little attractive forces they have to overcome, so they can move freely within the container. And since they don't have these attractive forces, they can kind of move through each other in a continuous fashion because there's large spaces between the molecules, because the actual molecules make up a very little component of the overall volume of the container. So molecules will never come into contact with each other. So very far apart. Now, compared to liquids and solids, gases have very low densities. The unit of density for a gas is typically grams per liter. So the density of the gas is very low compared to densities of solids and liquids. We talked about gas pressure. Now, the third part or component is very important. Gases behave most ideally at low pressure and high temperature. So the lower the pressure of the gas and the higher temperature you keep it at, the more ideally it'll behave, meaning as we talk about these individual gas laws, as they behave more ideally, they'll follow these trends. And so the low pressure means that molecules of gases are very far apart, so there's no attractive forces. High temperature means they're moving very fast. So again, there's no interaction with other molecules, so this makes it behave more ideally. So this brings us to our first gas law, talking about how two properties are interdependent on one another. And in Boyle's law, we're discussing how pressure and volume are interdependent. And so here it says volume of a gas varies inversely with the pressure exerted by the gas. And again, temperature and moles are held constant. So there's no change in temperature, no change in the amount, but if you increase the volume, the pressure will react inversely. So what that means is as we increase volume, that's going to cause pressure to decrease. As we decrease volume, it's going to cause pressure to increase. So this is the only law that's inversely related. And so you get what's called down here Boyle's law, where if you take the pressure and the volume of a gas at a constant temperature in moles, you get a constant. And so what happens is if you rearrange this and you write P equals K divided by V, and you plot the pressure versus 1 over V, you'll get a linear line. And so the slope of this line would equal the K. So again, if you plot pressure versus 1 over volume, you're going to get a linear line, and the slope equals K for that system. And so this is graphically showing you what happens as you plot pressure and 1 over V. Now, pressure can be in any unit, and volume can be any unit for Boyle's law. There's no requirements for units with this law. The obvious question is, what happens if we change the pressure? How do we find out what the new volume is? And what we do is we use this equation PI/VI equals PF/VF. So we know the initial pressure and volume, and we want to change the pressure, we can calculate the new volume. If we want to, if we know the pressure and volume initially, and we want to change the volume, we can calculate the new pressure. So this is the equation we're going to use to calculate what the new pressure or volume will be from its initial values. And so down here in the cartoon, what you're seeing is that initially we're at 1 atmosphere and 10 liters. And by the way, the orange color inside the cylinder represents constant temperature, and the number of molecules represents constant, or the number of spheres represent constant moles. So what we're doing is, as we increase pressure, we're seeing a decrease in volume. So if we double the pressure, the volume decreases by half. If we quadruple the pressure, the volume decreases by a fourth. Because as pressure increases, the volume decreases. Now we're going to look at some examples involving this. So here we have a gas that occupies 10 liters at 1 atmosphere. What is the, if we decrease the pressure to 2 atmospheres, what would cause, it would cause the volume to become what? So we want to find the final volume when we increase the pressure from 1 atmosphere to 2 atmospheres. So we start at 10 liters in 1 atmosphere. If we increase the pressure, what would the new volume be? What we're going to be using is that P initial, V initial equals P final, and V initial. Let's set that up. So usually I like to use a table. So we have pressure and volume. So we have the initial, the final, and our prediction. Yeah, oh, that's correct. Yeah, it should be increasing. My bad. We increase. So initially our pressure is 1 atmosphere. Our volume is 10 liters. In our final state, our pressure is increased the 2 atmospheres, we're looking for the new volume. So what we know is that pressure increased. So that's our prediction. Pressure increases. So what should volume do? Volume should decrease, because if pressure increases, it's inverse to volume. Volume should decrease. So the volume of our gas should be less than 10 liters. Now when we set it up, remember it's PI VI equals PF PF. So we put in 1 times 10 equals 2 times VF. So to get rid of the 2, we have to divide each side by 2, and we get VF equals 1 times 10 divided by 2. And this would be 5 liters. So just like we predicted, if pressure increases, volume should decrease. We'll look at some more examples of this law, and then we'll take a brief minute if there's any questions. This was one example. Look at 2 more examples. So here we have a 5-liter sample of gas at 25 degrees Celsius and 3 atmospheres. It is compressed at a constant temperature to a volume of 1 liter. What is the new pressure? So again, if we draw our little table, you don't have to do the table if you don't like. I just like doing it because you can see everything. We have pressure, we have volume, initial, final, and prediction. So initially our pressure is 3 atmospheres. And again, for pressure and volume, you don't need any certain units. As long as they're in this, both pressures are the same unit, it's okay. And then volume is 5 liters. In our final state, the volume is 1 liter, and we don't know the pressure. So in this example, you see that volume decreased. So we predict that pressure should increase, because again, it's inversely related. Now if we set up our equation, we need to solve for the final pressure. So we divide both sides by 1. We get 15 atmospheres. So we see that the pressure increased when we went from 5 liters to 1 liter, because pressure and volume are inversely related. In our second example, we have 3.5 liter sample of gas at 1 atmosphere. It expands at a constant temperature until the pressure is 0.1 atmospheres. What's the volume of the gas? Again, we're at constant temperature, and pressure and volume are changing. So we draw our little chart. So initially we have 1 atmosphere, and 3.5 liters. In our final state, the pressure is 0.10 atmospheres. But we're still looking, we need to know the final volume. So our prediction, we notice that pressure decreases, so volume has to increase. So now when we set up our equation, we got 3.5 times 1 equals 0.1 times V final. And we get V final 3.5 times 1 divided by 0.1. Again, the 0.1 we have to move to the other side. We do that by division. And we get 35 liters. So the volume did increase when the pressure decreased. So the next law looks at volume and temperature. Remember, Boyle's law looks at volume and pressure. Charles's law, and by the way, these scientists were around. We're looking at the time period of the 16th, 17th, 18th centuries in Europe. You know, that's around the time when these laws were coming about. So with Charles's law, volume is directly varies with absolute temperature. Now for Charles's law, the temperature always has to be in Kelvin. And just a refresher of what Kelvin is, Kelvin equals 273.15 plus the degrees Celsius. So anytime you use temperature in the gas chapter, it has to be in degrees Celsius. And so varies directly. What that means is as we increase volume at constant pressure in moles, we're going to increase temperature. If we decrease volume, we're going to decrease temperature. And so what we get is Charles's law at the bottom. So notice the slight difference between Charles's law and Boyle's law. Boyle's law was V equals K. Charles's law is V over T equals K. And so if we rewrite this, V equals K times T. If we were to plot volume versus temperature, we would get a linear relationship, and the slope equals K. So again, we plot volume versus temperature, whereas you saw on the previous slide, it was a little bit different. So this is what a Charles law graph looks like. So now let's see what happens if we change the temperature. How will we calculate the new volume? And so we would use this equation here. Notice the difference between Boyle's law. So VI over TI equals VF over TF. Again, temperature has to be in Kelvin. So here, as we start with 1 atmosphere, 1 liter, 273 Kelvin. We increase the temperature, the volume increases. So we double the temperature, we double the volume. If we quadruple the temperature, we quadruple the volume. So it's a 1-to-1 relationship. So let's look at an example of Charles's law. So we have a gas occupies 10 liters at negative 10 degrees Celsius. If the temperature increases to 60 degrees Celsius, it would cause the volume to become, and we have to calculate what the new volume would be. So it's going to be a very similar setup to Boyle's law. Let me start over here. We're going to have V and T. Initial, final, prediction. So initially, we have 10 liters and negative 10 degrees Celsius. Now, if the temperature increases to 60 degrees Celsius, what's the new volume? And so here we notice that temperature increased, so we predict that volume should also increase. Because if temperature increase, volume should increase according to Charles's law. Now, before we start plugging and chugging, we need to convert the temperatures to Kelvin. So we have T initial, 273.15 minus 10. And we have T final, that's 333.15. So now we have both the temperatures in Kelvin. Now we can put them into the equation. But remember, this equation was different. It was V initial over T initial equals V final over T final. So we were to set this up. So it would be 10 divided by 363.15 equals V final divided by 333.15. Notice that if we kept the temperatures in degrees Celsius, we would have ended up with a negative volume. And you can't have a negative volume. So to move the 333.15 to the other side, we're going to multiply each side by 333.15, and we get V final equals 10 times 333.15 divided by 263.15. And if we did it right, our prediction says it should increase. So we should see a volume greater than 10. And we get a volume of 12.7 liters. So just like we predicted, it increased. So we're going to look at a few more examples involving Charles's law. Going on to the next examples. So in the first example, we have a 2.5 liter sample of gas at 25 degrees Celsius. It's heated to 115 degrees Celsius at constant pressure. What is the new volume of the gas? So again, you may be wondering, well, how do I know we're using Charles's law, even though it says practice with Charles's law? And what you can look at is we start with a volume and a temperature, and it says it's heated to 115 degrees. So volume has changed, and it also mentions at constant pressure. And then it wants to calculate the new volume. So here we see that volume and temperature are changing. This indicates that it has to be Charles's law. So we'll set up our little table. And we have volume, temperature, initial, final, prediction. 2.5 liters, 25 degrees Celsius, 115 degrees C, and question mark for the final volume. So here we see temperature increase. So volume should also increase. So it's a direct relationship. But before we begin plugging away, we have to convert temperatures into Kelvin. So T initial, we got to add 273 to it. And T final, we add 273 to it. We get 388.15. Now we have our temperatures in Kelvin. We can set up our equation. Remember, it's V initial divided by T initial equals V final divided by T final. Now again, since the 388 is on the bottom, we need to multiply both sides by 388 to move it to the top. So V final equals and our new volume is 3.3 liters. So just like we predicted, when temperature went up, the volume also increased. Now, so far, we've just been calculating the final volume. In the next example, we want to calculate what's the new temperature when we compress a sample of gas at 6.7 liters and 55 degrees Celsius to 1.2 liters at a constant pressure. What's the new temperature of the gas? So again, we do our little table. So our initial volume, 6.7 liters. Our initial temperature, 55 degrees Celsius. Final volume, 1.2 liters. And the final temperature is what we're looking for. Now the final temperature needs to be in, remember, degrees Celsius. So here we're decreasing the volume, so our temperature should also decrease. Now before we begin, we got to convert temperature into Kelvin. The reason Kelvin's called absolute temperature is because it cannot be negative. Before we begin plugging away, just to show you, now we have V initial over T initial equals V final over T final. Again, what we're looking for is T final. But notice here, T final is on the bottom. So we have to move it to the top. So to move T final to the top, we got to multiply both sides by T final, because it has to be on top for us to solve it. And you only do this when you're looking for T final. So when you multiply both sides by T final, these two T finals cancel and we get T final times V initial over T initial equals V final. Now you can continue to reduce it and move stuff to the other side, but what I want to do is I want to put it in numbers, and then at the end we're going to move this number here to the other side. So we have T final times D initial divided by T initial. And then we have it equal to V final, which is 1.2. So now what I'm going to do is I'm going to take 6.7 and divide it by 328.15. And I get 0.0242 equals 1.2. So now notice, to get rid of this 0.02042, we have to divide both sides by it. So now T final is 1.2 divided by 0.02042. And we get 58.8 Kelvin. And now we need to convert this to degrees Celsius. So to convert it to degrees Celsius, be 273.15 minus 58.8. And we get 214 Celsius. So that's the final temperature. Did something wrong. Let me go back and check. Oh, that's where I made my mistake. Yes, this is actually 6. Thank you. Let's see. So 1.2 divided by 0.02 Okay. Backwards 58.8 minus 273.1. And we get negative 214. That makes better sense. So you notice it's less than our initial temperature. So as we decrease the volume, the pressure also decreases. Before we ask for questions, so I want to give you an example of a real life example of Charles's law. If you ever get bored one day and you want to see Charles's law in action, what you can do is if you blow up a balloon, if you can use helium, it'd be better, but if you can't, you can use air. Blow up a balloon and stick it in the back of your freezer and just leave it there for about 2, 3, 4 weeks. And when you open it after about 2 to 4 weeks, you'll notice that the balloon has shrunk. Because what's happening is the balloon has a constant pressure because it's tied up. It has a volume and it has temperature. When you put it in the freezer, what happens is the temperature of the gas inside the balloon decreases, causing the volume to decrease. So over time, your balloon will shrink. If you ever have the chance to get some dry ice, you can do this same experiment, but with dry ice, it works a lot faster. Dry ice is a lot colder than your freezer. Thus, if you ever want to see Charles's law in action, you can do that experiment. So far we've looked at 2 gas laws. We looked at Boyle's law, which shows how pressure and volume are interdependent, a constant temperature and amount. And we looked at Charles's law, which talks about how volume and temperature are interdependent at constant pressure and amount. So the only property of a gas we haven't touched on is the property of amount. So the next gas law shows you how the amount of a gas changes with volume. And another type, well, I was a little bit off on that, it's the one after this, but the combined gas law actually combines Boyle's and Charles' law to talk about what happens if we're changing the pressure, volume, or temperature, and one of these is constant. So, or one of these is changing. Oh, excuse me, all 3 of these are changing. And so from that, we can calculate either the new pressure, volume, or temperature. So again, with the combined gas law, what we're doing is we're combining the 2 laws we just talked about into one law. So Boyle's law and Charles's law combined into the combined gas law. And so here, what's different about this one is that 3 variables are changing, whereas in the other 2, 2 variables were changing. And so here, if we look at a problem involving the combined gas law, what you'll notice is that we have 3 variables changing, not just 2. So we have a sample of nitrogen gas, has a volume of 1.2 liters at 35 degrees Celsius and 2.5 atmospheres. If we decrease the temperature to 15 degrees Celsius and pressure is increased to 4.7 atmospheres, what's the new volume of a gas? So here you'll notice that liters, or volume, temperature, and pressure are all changing. So this is a good indication that you have to use the combined gas law. If only 2 variables are changing, that's going to be an individual gas law. And so we'll set up our table again. But instead of 2 things, we're going to have 3. So we're going to have pressure, volume, and temperature. Initial, final, prediction. Now here, sometimes the prediction can be inconclusive if two of the variables that are changing have opposite trends. So what that means is pressure is increasing and volume is increasing. Well, they don't go together. So then therefore to predict temperature would be inconclusive. So here our initial pressure, 2.5 atmospheres. Volume is 1.2 liters and 35 degrees Celsius. Final pressure, 4.7 atmospheres. Volume is what we're looking for. And temperature, 15 degrees Celsius. So here, we notice that pressure increases because it went from 2.5 to 4.7. Here we notice temperature decreases from 35 to 15. So we need to predict what will volume do. So if we remember with Boyle's law stated that if pressure increases, volume would decrease. And Charles's law states that if temperature decreases, volume would decrease. So since both of these laws are predicting volume to do the same thing, we can predict that volume should increase. Now, if one of the laws said volume would increase and the other one said volume would decrease, then it would be inconclusive. But the fact that both of them suggest that volume will decrease means that the volume in this example should decrease. Again, if one said increase and the other said decrease, then it would be inconclusive. So they both have to be telling you the same thing in order to predict it accurately. If they're not, it's inconclusive. You can't do a prediction. So before we begin, we have to convert our temperatures into Kelvin. Now, if we remember, it's PI/VI divided by TI equals PF/dF divided by TI. So what we're looking for is VF. And so I'm going to simplify this a little bit. So I'm going to do the operation on the left side. And we get 0.009735 Then on the right hand side, I'm just going to take 4.7 divided by 288.45. And we get 0.0163 times VF. So now, to find VF, we need to divide both sides by 0.01631. So when we do that, we get 0.6 liters. So we initially started at 1.2 liters. We increased the pressure, decreased the temperature. Our volume, as predicted, decreased to 0.6 liters. We'll look at one more example involving the combined gas law. So we want to calculate the temperature when 1.3 liter sample of gas at 1.7 atm and 90 degrees Celsius is compressed to 0.75 liters of gas at 2.6 atm. Again, we'll draw our table. We have pressure, volume, temperature. We have the initial, final, and our prediction. So again, we know that it's the combined gas law, not just because the title says so, but you see that three properties are changing. And so we have 1.7 atmospheres, 1.3 liters, 90 degrees C, 2.6 atmospheres, 0.75 liters, and question mark. So here we notice that pressure is increasing and temperature, we don't know, but volume is decreasing. So we don't know how pressure relates to temperature, because if we increase pressure, we didn't see a law that relates pressure and temperature. But with volume, we know that if we decrease volume, temperature should also decrease. But with pressure, we don't know if when we increase pressure, what should happen to temperature, because there's no law that we've covered that shows a relationship between pressure and temperature. So therefore, it's inconclusive what temperature will do. So we need to make sure that we do our calculation correct. So we need to convert Ti into Kelvin. And now we're going to solve for T5. So remember, it's V initial, or T initial equals V final, P final over T final. So what I'm going to do first is I'm going to solve for this, get this number, and then get this number. And then I'm going to multiply both sides by T final to move T final over here, and then divide by this number to move it over here. So let's look at that worked out. 3 times 1.7 + 363. What I'm going to do is I'm going to multiply out all the numbers to get two numbers on both sides, and then we'll move it around to solve for T final. So notice here at this point, T final is on the bottom. So the way we move T final to the other side is we multiply both sides by T final. And you see that T final on this side cancels. Now to get T final by itself, we need to divide both sides by this 0.0060856. And this should tell us T final in Kelvin. Again, the reason we divided both sides by 0.0060856 is so they cancel out on the left side, and we're just left with T final. And we get 320.4 Kelvin. Now we're going to convert this to degrees Celsius. And we get 47.3 degrees C. So in fact, the temperature did decrease. So the last law that we're going to talk about in regards to individual laws is Avogadro's law, which relates to the last property we haven't talked about, which is moles. So Avogadro's law says that if you have equal volumes of an ideal gas, they're going to contain the same number of moles if measured under the same conditions, aka temperature and pressure. So what happens is, if you look at the Avogadro's law, which is V over N equals Ka. So what this means is, as we increase the volume, we're going to increase the moles of gas at a constant temperature and pressure. So we can rewrite this. We rewrite this equation as V equals K to the N and we graph it, it would look something like this. So we plot volume versus moles. The slope equals, okay. So there's a direct relationship between the volume and the moles. And like Charles's law, the equation to calculate the final moles or final volume when you change one of the properties is shown here. So again, Avogadro's law relates amount to volume. So we'll look at one problem involving Avogadro's law. We have 5.5 moles of carbon monoxide at 20.6 liters. How many liters will 16.5 moles of carbon monoxide occupy at the same temperature and pressure? So when we read this problem, we notice that we're looking at two variables that change, moles and volume. So that's why we're using Avogadro's law. Temperature and pressure are constant. So now we draw our little chart. So our initial volume is 20.6 liters. Moles is 5.50 moles. Final volume, we don't know. Final moles, 16.5. And so here you'll notice that we increase the moles, so we predict that the volume will also increase. Now we're going to use that equation VI over NI equals VF over NF. And we don't have to worry about the units. We can use moles and liters, that's fine. So we get 20.6 divided by 5.5. To solve for VF, we have to multiply both sides by 16.5, and we get VF equals so if we did it right, the volume should increase. And we get 61.8 liters. So again, with these individual gas laws, which ones we need to use is based on what two properties are changing, what properties are held constant. For the combined gas law, we're looking at three properties changing: volume, pressure, and temperature. That's a good indication of when to use that law. Now, you don't have to, again, memorize the equations. You just need to know how to utilize the equation and know which equation goes with which law. Now, one other interesting fact about gases is that we have something called the molar volume of a gas. And so the molar volume of a gas is the volume that 1 mole of gas occupies at standard temperature and pressure. And so as you read about gases and experiments involving gases, you're going to often read about STP conditions. So STP conditions means standard temperature and pressure. So the standard temperature is 273 Kelvin. The standard pressure is 1 atm or 760 millimeters of mercury. So whenever you're reading about gases and it said, hey, this experiment occurred at STP, or this gas expanded at STP, it means that the temperature is 273 Kelvin or 0 degrees Celsius, and the pressure is 1 atm, which is also 760 millimeters of mercury. So at these conditions, 1 mole of gas occupies 22.4 liters. So if 1 mole of gas is 22.4 liters, you can imagine 2 moles of gas would be 44.8 liters, and 3 moles of gas. So all we're doing is taking the moles and multiplying it by 22.4. Would be 67.2 liters. So if you're at STP, it's very easy to find the volume of a gas. Once you know the moles, it's just taking the number of moles and multiplying it by 22.4. So this is what we refer to as the molar volume of a gas at STP. 1 mole of gas occupies 22.4 liters. Very important that you remember the standard temperature and pressure of a gas. So now we've talked about Boyle's law, we talked about Charles's law, we talked about Avogadro's law. So just like the little groups on Lord of the Rings, we had the humans, the elves, and the dwarfs. They all combine for one ring to rule them all. Just like here, we take all these gas laws, we make one law to rule them all. And so that's called the ideal gas law. So when we use the ideal gas law, we're not changing properties. We're saying if we have this volume, temperature, and moles, what's the pressure of this gas? Or if we have this pressure, moles, and temperature, what's the volume of this gas? So when we use the ideal gas law, no property is changing. We're given 3 of the properties and asked to calculate the 4th property. And we can derive all the ideal gas laws, or excuse me, we can derive all the individual gas laws from the ideal gas equation. So it's kind of like a culmination of all 3 of these laws. Now, just a few things when we use this law, a few important things. Temperature, of course, has to be in Kelvin. So anytime you use the ideal gas law, temperature has to be in Kelvin, volume has to be in liters, pressure has to be in atm, and of course amount has to be in moles. These are a must when using the ideal gas law. And the reason is because if you notice in the ideal gas law, or some people like to call curve nerd, to remember it, we have this variable R. And so R is referred to as the ideal gas constant. And its value is 0.0821 liter atmosphere per mole Kelvin. So due to the fact that the units of the ideal gas constant is in liter atmosphere per mole Kelvin, that's why we have to have all those properties in those particular units when we're utilizing the ideal gas law. So you don't have to remember the ideal gas constant, you just have to know to use it and to make sure that the other properties are in the correct units before you start doing calculations. So again, with PV equals nRT, no property is changing. You're given 3 of the properties and asked to calculate the 4th property by rearranging this equation. So again, R is the gas constant, 0.0821. The units, liter atmosphere mole Kelvin. That's why we have to have the pressure, temperature, volume, and moles or amount in these particular units. Very important. So here, let's look at 2 examples involving the ideal gas law. First, we want to know what volume of gas occupied by 5 grams of methane at 85 degrees Celsius and 650 millimeters of mercury. So we have this gas, we have 5 grams of it, it's at 85 degrees Celsius, 650 millimeters of mercury. What volume does it occupy? So notice here that nothing is changing. We're given 3 properties of gas, and we're asked to calculate the 4th property. So what we're looking for is volume. If we remember from the ideal gas equation, PV equals nRT. So to solve for volume equals nRT divided by P. So if we know the pressure, we know the temperature, and we know the moles, we can calculate the volume. And again, the volume will be in liters. So remember, R is the gas constant. We got that. Temperature needs to be in Kelvin. We can do that. So that's checked off our list. Pressure needs to be in atmospheres. So the way we do that, since we're starting with millimeters of mercury, we need to divide by the 760 millimeters of mercury equals 1 atmosphere. So that's the conversion here. "760 millimeters of mercury equals 1 atmosphere." So if we're going to convert millimeters of mercury to atmospheres, we need to divide by 760. And make sure when you divide for the pressure, you don't round too much. Get 4 or 5 significant figures, because if you round, it could cause a lot of error in your answer reports. And we get 0.855263 ATM. The last thing we need to do is thanks. Made a typo here. It should be 85. This would be 358. 115. The last thing we need to do is find the moles, and you'll notice that it's given us the mass of methane. So if you remember back in the earlier chapters, when we had mass, the way we find moles is dividing by the molar mass of methane. So the molar mass of methane would be one times 12 plus 4 times 1. And this would be 16 grams per mole. So to find the moles of methane, we need to take 5 divided by 16. Get 0.3125. Now all of that was just to get everything in the right units. Now we need to plug it into volume equals nRT divided by P. This will put volume in liters. I get 10.7 liters. Let me double check. So again, the way you know when to use the ideal gas law, it gives you 3 of the properties of a gas and asks you to calculate the 4th property. Now we look at example 2. In example 2, we want to know what mass of nitrogen gas is required to occupy 2.8 liters at 100 degrees Celsius and 920 millimeters of mercury. So what we're looking here for is mass. But if we look at our ideal gas equation, we have PV equals nRT. So mass is not found in the PV equals nRT equation. But what we know about mass is equal to the moles times the molar mass. So if we know the molar mass and we know the moles, we can calculate the mass. And the molar mass we can find from the periodic table. (28 grams per mole). But the moles is what we need. So now we have to use the PV equals nRT equation because we know the volume of the gas, the temperature of the gas, and the pressure. We can solve for moles. So moles equals PV divided by RT. But again, before we start plugging and chugging, we need to get everything in the right units. So pressure, 920 millimeters of mercury. We need to divide by 760 to get atmospheres. So we get 1.2105. That's one thing out of the way. Volume is in liters, so we want to change that. That's good. The temperature needs to be in Kelvin, so we have 100 degrees Celsius. And then lastly, R, 0.0821 liter atmosphere per mole Kelvin. Now we have everything in the right units. We can solve for moles. So the 760 is what we use to convert millimeters of mercury to atmosphere. So if you look up here in the top right hand corner, we see that 760 millimeters of mercury equals 1 atm. So we need to convert the millimeters of mercury to atm by dividing by 760. So anytime you use the ideal gas equation, you always have to be in atmospheres. Double check my work. Yeah. So now we have the moles of gas. To find the mass, we just need to multiply the moles by the molar mass. And we get 3.10 grams of nitrogen. So again, when we're using the ideal gas equation, 3 of the properties are given to us. We need to calculate the 4th property. Second is, you need to make sure pressure is in atmospheres, volumes in liters, temperature is in Kelvin, and then you can plug everything in and solve for the property you're looking for. And so these are all the laws that kind of relate all the different properties of a gas.